The St. Lucie Canal, a window into deep time. When the Everglades Drainage District cut the St. Lucie Canal between 1916 and 1924, they unknowingly created a 23-mile geologic cross-section through Florida's coastal plain. That canal cut, later widened and renamed C-44, exposes the subsurface stratigraphy in its slopes. If someone built a walkway along the canal walls, you'd have a Disney-esque ride through 125,000 years of geologic history. And right there, between elevations 19 and 21 feet, sits a distinctive sand lens, ancient storm deposits from hurricanes that battered this coast during the last interglacial. During marine isotope stage 5e, roughly 125,000 years ago, sea levels stood 20 to 25 feet higher than today. The Atlantic Ocean lapped against what we now call the Green Ridge, Florida's ancient barrier island. A washover fan forms when hurricane storms surge overtops a barrier island, carrying beach sand landward in a powerful surge of water. As this surge crosses the ridge crest and enters the quieter back barrier lagoon, it loses energy rapidly. The sand drops out of suspension, spreading into a fan-shaped deposit. The resulting sediment has a distinctive signature, coarser than typical lagoonal muds because it originated as beach sand, but slightly finer and better sorted than in-situ beach deposits due to the winnowing action of transport. It sits right between the two end members. These samples from the C-44 STA cells match that washover fan gradation almost perfectly. Physical evidence of ancient hurricanes that battered Florida's coastline during the last interglacial, preserved beneath the modern landscape for over 100,000 years. The St. Lucie Canal, also known as the C-44 Canal or simply C-44, is a man-made canal in Martin County, Florida, connecting Lake Okeechobee to the Indian River Lagoon. The canal was built between 1916 and 1924 to divert floodwaters from the lake into the St. Lucie estuary via the South Fork of the St. Lucie River. Deepened in 1937 to enable the passage of boats, the St. Lucie Canal is now the eastern segment of the Okeechobee Waterway. The St. Lucie Canal connects to Lake Okeechobee at Port Mayaca, Florida. The canal is 8 feet deep as a result of its second deepening in 1949. It has a rate of flow of 9,000 cubic feet per second. In 1933, 16 fixed spillways were approved for construction to reduce shoaling caused by flow out of the sand lens. In 1924, the canal's original flow capacity was 5,000 cubic feet per second. In 1937, the canal was deepened to 6 feet, increasing its flow capacity. In 1949, it was deepened to 8 feet, which increased the flow capacity to 9,000 cubic feet per second. The sand lens is exposed in this canal cut, and it is very easy to define by looking at the steep slope segments of the canal from the 2020 USGS point cloud data. The steep part of the slope reflects the instability of the sand lens, and it is very easy to identify from the USGS Advanced Viewer, which has a slope layer.
जब मुझे तुझको देखे है छुप के, तेरी सहेलियों ने बता दी तेरी बात। तू भी पगली मैं भी पगला। ला 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 ला, तू भी पगली मैं भी पगला। ला 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 ला, तू भी पगली मैं भी पगला।
Beach sand, lagoon sand, and overwash fan sand. Understanding sediment gradation. Beach sand, back barrier lagoon sand, and overwash fan sand each tell a different story about wave energy and sediment transport. The key to understanding their different gradations lies in the energy of the water that deposits them. Beach sand forms in the highest energy environment. Powerful ocean waves constantly crash onto the shore, winnowing out the fine particles like silt and clay, carrying them away in suspension. Only the heavier, coarser grains, typically medium to coarse sand, can settle and remain on the beach face. This constant wave action creates well-sorted sand, meaning the grains are remarkably uniform in size. Walk on a beach and you will feel this consistency beneath your feet. Back barrier lagoon sand exists in a completely different world. Protected behind the barrier island, the lagoon experiences minimal wave energy. Without vigorous waves to sort the sediment, the lagoon accumulates a mixture of grain sizes, fine sand, silt, clay, and organic material. This poorly sorted sediment often feels muddy or silty. The water is calm enough that even the finest particles can settle out of suspension and remain on the bottom. Overwash fan sand, also called washover fan sand, represents a dramatic event frozen in the geological record. During major storms, waves overtop the beach ridge or dune crest and surge landward into the back barrier area. As this sheet of water flows inland, it carries a sediment load with it. But here is where the gradation becomes fascinating. As the flow spreads out and loses energy, the heaviest grains drop out first, near the breach point. Medium grains settle further inland. The finest grains travel the farthest before finally settling at the distal, or far end, of the fan. The result is a distinctive fan-shaped deposit that grades from coarser sand near the beach to finer sand toward the lagoon, a permanent record of the storm that created it. Whitehaven Beach, a window into ancient Florida's white sand lagoons. Whitehaven Beach, located in the Whitsunday Islands of Australia, stands as one of Earth's most spectacular natural wonders. A 7-kilometer stretch of sand so pure white, it almost appears unreal. The secret lies in its composition. 98% pure silica quartz. This exceptional purity means the sand contains virtually no organic material. No shell fragments, no heavy minerals, just pure white quartz grains worn smooth over geological time. What makes Whitehaven's sand particularly remarkable is its fineness and its behavior. The grains are so fine and pure that the sand does not retain heat, remaining cool even under the blazing Australian sun. The sand squeaks audibly when you walk on it, a phenomenon caused by the friction between these remarkably uniform quartz grains. Its purity was so renowned that during World War II, the sand was actually mined to manufacture optical lenses. This may have been what Florida's back barrier lagoons looked like during marine isotope stage 5 echo, that warm interglacial period 130,000 to 80,000 years ago when sea levels stood 15 to 20 feet higher than today. Behind the ancient barrier islands, protected lagoons would have accumulated brilliant white quartz sand washed over from the beaches during storms. Unlike modern Florida beaches with their mix of quartz and shells, these ancient overwash fans and lagoonal deposits would have been dominated by pure quartz, the fatal beauty sand of a vanished coastline. Fatal perhaps because this landscape was doomed to disappear when sea levels fell again, leaving only subtle traces in the modern topography for us to decipher today.